Alright, students, welcome back to the continuation of our lecture on Unit 5, Machinability. Okay, so we were talking about metal cutting. We spoke about the different angles, side cutting edge angle, and back rake angle, positive back rake angle, negative back rake angle, side relief angle. Like I told you, yeah, every cutting tool, whether it's a lathe cutting tool, a milling machine cutting tool, all cutting tool comes with a tool geometry, meaning that it is associated with certain angles, and all these angles have a contribution to a good cutting. At the same time, we spoke about the use of coolant. There are several uses of coolant. Make sure you know at least 2 or 3 of it for your final exam. We also spoke about orthogonal cutting. If you remember, orthogonal cutting is the simplest form of cut. When you cut something into a half, like you take an apple, you cut it into half. In layman's term, we say cut. In technical term, we say we call it orthogonal cutting or shearing. Yeah. So we also spoke of the presence of frictional force. So during cutting, when the tool rubs against the surface, you have frictional force. You have a normal force generated, and the process of cutting itself, you have shear force. So all this contributes towards your machining operation. Okay, so let's look at the next topic, machinability. What is machinability? So as an industrialist, or if you go down to the manufacturing floor and you ask the people working over there, yeah, you ask, is this product a good machinability? Do you think that this product has been machined well? So most of the time, what comes to your mind firstly would be the appearance of the product. The product may look extremely good, excellently good, but can you say that that product had a good machinability? No. Okay. In your opinion, a good machinability may be just a good surface appearance. In someone else's opinion, a good machinability may be the functionality of the product. So it's very difficult for you to come up or to define the term good machinability or bad machinability on your own. So if given a scenario, okay, if I give you a scenario, I would expect you to define machinability in terms of 4 factors, and you would see this right now. Okay, so machinability or ease of machining is influenced by the kind and the shape of the cutting tool. Yeah, so 2 factors that affect machinability are the ductility and the hardness. Okay, so when I say machinability is better when the material is ductile, do you agree with me? Okay, if your material is ductile, soft, machinability becomes a lot more easier compared to when you're dealing with a hard or a brittle material. So like I mentioned to you earlier, good machinability does not mean a good surface finish or low forces and long tool life. Sometimes it refers to cost associated and the power consumed during a machining process. Okay, so good machinability can be defined in terms of 4 factors. Okay, first of all, tool life. Okay, tool life. So upon machining, is your tool life still good? Meaning that is your tool still sharp? Okay, so upon machining, is your tool life still good? Number 2, surface finish. Upon machining, is the surface finish of the product still good, smooth, or is the surface rough? Number 3, upon machining, what was the cost involved in the entire production? You may have an excellent, good surface finish with excellent tool life, but if the cost is extremely high, would you consider that as a good machinability? No. So a good machinability would involve low cost, and the 4th factor would be the power consumed. Okay, so upon machining, is the power consumption to produce that one product low or high? If the power consumption is relatively low, then we would consider it as a good machinability. So again, how do you define a good machinability? A good machinability will involve 4 factors. Number 1, tool life. Okay, upon machining, the tool that is used to manufacture the product has got good life. Number 2, the surface finish of the product. The surface finish of the product is good and smooth upon machining. Number 3, the power consumption. The power consumption is relatively low to machine that one product. And number 4, the cost of machining is relatively low to machine that one product. If given a case scenario, I would expect you to explain to me machinability in terms of these 4 factors, which is number 1, tool life, number 2, surface finish, number 3, power consumption, number 4, cost involved. Okay, so if these 4 factors have been fulfilled satisfactorily, then we would say that the machinability is good. If ever any one of these factors are lacking or missing, we would not consider that product a good machinability. So I would expect you to explain to me machinability in terms of these 4 factors. Please remember that in exams, the moment I give you 2 marks for a structured question, I may just give you a case scenario in an industry. A product has been machined, the tool broke during the machining process, the surface was rough, the cost involved overall was high, and the power consumption was high. I would not consider it as a good machinability, and I expect you to explain to me in terms of these 4 factors. So I would expect an answer as such. This product has got bad machinability because upon machining, the tool life is low, the tool has broken, yeah. The power consumption was high, so I wouldn't consider it as a good machinability. Cost involved was relatively high, and the surface finish was rough. So I would consider this product a bad machinability. I would expect that kind of an answer from you for 4 marks. Okay. Next, how do you measure the forces that are involved during a cutting process? Yeah. So during the cutting process, so I mentioned to you there's like several forces involved. Yeah, you have the shear force, you have the frictional force, you have the normal force. Okay, verbally I can say frictional force is high. What do you mean by high? How much is high? How do you measure this? Okay, so you can use a dynamometer to record the tool forces in a particular cutting condition. So you'll be able to detect what is the frictional force generated, or how much frictional force is generated, how much shear force is generated, and so on and so forth. Our next topic is tool life. What is tool life? Okay, so tool life generally, when we talk about tool life, we are very obviously or very often we only talk about one kind of tool life, which is abrasive wear. Abrasive wear is as you cut and cut and cut and cut, eventually the tool will become blunt, tumpul. So that in technical terms we say abrasive wear. In layman's term we say the tool has become dull or the tool has become blunt. So when does this happen? Yeah, abrasion wear is caused by small particles of the workpiece rubbing against the tool surface. So as the particles rub against the tool surface, rub, the tool will eventually and slowly wear off, and it will lose its characteristics, and then you need to go and resharpen the tool again. So that is abrasion wear. Number 2, adhesion wear. What causes adhesion wear? Adhesion wear is caused by a welding action on the surface of the tool and workpiece. Meaning that if you remember, we spoke about built-in edge chips. Remember when I told you that when you're machining a overly ductile material, there are times when the chip have the tendency to weld against the tool. Okay, so when this kind of phenomenon occurs, I told you that the tool cannot be used anymore. The moment the chip welds against the tool is considered damaged. You cannot use it. So we consider this as an adhesion wear. Adhesive dia melekat. So we consider this as an adhesion wear. Number 3, diffusion wear. What is diffusion wear? Right from the beginning of the lecture, I keep telling you, your tool, cutting tool, and your material of cut has to be compatible. If there is incompatibility, what would happen? Either your tool will bend or your tool will break. So diffusion wear is a gradual deformation of the tool surface. If your tool bends or breaks during the cutting process, we consider it as a diffusion wear. Chemical and electrolytic wear. What is a chemical or electrolytic wear? It's a reaction between the tool and workpiece in the presence of cutting fluid. So, chemical and electrolytic wear occurs when there is some chemical reaction between the tool and workpiece. So for example, if you're cutting aluminum and your cutting tool is made out of material that's chemically reactive, so by the time you cut and finish the material, your aluminum material would have transformed to aluminum oxide at the point of cut, which is a no-no, a complete no-no, yeah. So chemical and electrolytic wear has to be avoided during a cutting process. Lastly, oxidation wear. Oxidation wear is the formation of rust. If your tool has rusted, we call it an oxidation wear. Oxidation wear is when your tool becomes rusted, becomes brittle, and it undergoes brittle failure. So you need to know these 5 wears. Okay, number 1, abrasion wear. Number 2, adhesion wear. Number 3, diffusion wear. Number 4, chemical and electrolytic wear. Number 5, oxidation wear. All these 5 wears actually present, is always present. It's just that the abrasion wear is very commonly spoken about. So we always think that the moment a tool fails, oh, okay, it's abrasion wear. No, okay. So there's 5 different kinds of tool wear that occurs, and these are the 5. Okay. Lastly, we have Taylor's equation. Taylor's equation basically shows the relationship between tool life and cutting speed. What is the relationship between tool life and cutting speed? So if you look at it, C, Vt to the power of n equals to C, where V is the cutting speed, millimeters per minute or meters per minute. T is the tool life in minutes. C is the constant for a tool life. Okay, so if you look at it, what is the relationship between cutting speed and tool life? Okay, so if you look at it, C equals to Vt to the power of n. So C over V equals to T to the power of n, meaning that T is inversely proportional to cutting speed. Do you agree? C. So C is inversely proportional to cutting speed. Do you agree? So meaning that as the cutting speed increases, what will happen to your tool life? If it's inversely proportional, meaning that cutting speed increase, tool life will decrease. Okay, so there is a graph that I always plot to show you, yeah. So you have the graph of